Hello, everybody, and thank you all of you for being here. Thank you also, Rahul, for accepting the invitation. Today, Rahul will give a talk about physics-informed neural network framework for unsteady discretized reducible systems. So please, Rahul, the floor is yours.
Yeah, thanks, Priya. Hello, everyone. So today I'll be talking about the topic we also told physics-informed neural network framework for unsteady discretized reduced order system. Mainly the goal of this work is that to apply for different practical industrial applications, although in this work I will show only the toy problems. So and the way of talking will be more on the application side than less mathematics probably. So let's go ahead. And so first, let's see why reduced order model. Very basics. Of course, all of our group members, if there are others, we know this kind of what is the context of it. But for general purpose, like if we have any physical process of any industrial interest or any kind of like aerospace, marine, biomedical. So of course, nowadays we are carrying out numerical simulation, and which is of course less time consuming than experiment, and it's very economically feasible. But main computational expenditure happens when there are some repetitive jobs involved, like in design, control, monitoring, etc. And And those high performance computational tools are also very time consuming at some point if the complexity of the numerical simulation becomes very high. So that's where the relevance of ROM development comes. Especially it helps in the exploration of the parametric space. So you can quickly predict the output over any parameter of interest. Once you have developed the reduced order model, then real-time analysis also possible, which helps in control of any industrial product. And we can carry out the simulation in a very small laptop without not that much computational power. So being said what is the general ROM framework and where exactly our discretized physics-informed neural network stand? So in the left-hand side, we have this projection-based reduced order model framework. So we need two things. One is some high-fidelity numerical simulation data. We call it as a full-order trajectories. Oh, whatever. Yeah, full-order trajectories. And also we need some set of governing equations which we project on a reduced space. So like we compute the operator from that, and then we can do Galerkin projection or LSTM projections. And from the full order trajectories as well, like the high fidelity simulation data, we can generate some linear manifolds or nonlinear manifold. So from the linear manifold, the techniques are like POD, reduced basis method, etc. There are a lot of nonlinear manifold projection techniques are also available nowadays. One of the ways autoencoder types nonlinear manifold projection. So coupling these two ways, one is coming from equations and one is coming from full order trajectories, you can generate projection based on order model. So and another area is the data-driven approach. Like one to project your high fidelity simulation on a reduced space using linear or nonlinear manifold techniques. You can learn the reduced dynamics using some data-driven approach. So like typically different machine learning approach, deep learning approach can be considered, like artificial neural network, ANN, GPR, radial basis function, LSTM, like that. So both the methods have pros and cons. And of course, in the projection-based approach, we have it is numerically not stable at some convection-dominated problems or some complicated problems. However, we need less amount of data because that is getting compromised. The data can be scarcity of data can be complemented by the equations.
there is a problem with the camera. And try to deactivate and to activate.
Okay.
Okay.
You can see.
Sorry.
Don't worry. Oh, perfect. Okay, so now our idea is that, okay, can we get the residuals obtained from those projection-based reduced order model and put it in the loss function of the deep learning-based deep learning data-driven approach. And this is what is the key idea behind this discretized physics-informed neural network. So what is the objective of this work? So there are, as I told you, like there are forward solvers available for doing CFD simulations like OpenFOAM, SU2, DEAL2, etc., whatever. They use this finite difference, finite volume, finite element approach. So they are physics-based, good for well-posed problems. But as I told, they are expensive for repetitive problems. But they give us very highly accurate predictions, but they are difficult for real-time data assimilations. On the other hand, data-driven approach are, on the other hand, it's good for in-post or inverse problems, but the prediction accuracy depend on the richness of the training data set. So our idea is that can these two areas be merged in the physics-informed neural network context? So when I say can these two areas be merged in the physics-informed neural network context, it means like for different complex geometry or large-scale problem, probably an industry or we have already set up all the forward problems already in our choice of interest in our favorite CFD solver. So that part I don't want to use it in the PINN anymore, those governing equations. I can directly take the residuals and can solve that complex problems. And using this framework, we can also solve, we can also use this for conventional forward solvers for inverse problem or optimization or any kind of ill-post problem as well. So that is the objective of this work. So I already have some forward solvers and use them, and everything has been set up for solving a problem, and use that residual in a PINN framework to solve some ill-post problems and use those kind of solvers. Okay, so and then any kind of this is the framework of a general nonlinear equations. Any PD can be cast into this kind of format. So where A is a linear operator and F is a nonlinear operator and B is acting on the input. And if we discretize it using any our favorite time discretization approach, say here, like I have shown, say for the time discretization, I have shown the backward Euler. And if we solve, and if we do the space discretization using implicit approach, it will look like this. And also if we discretize it using any explicit numerical approach, discretization approach, it will look like this. So it is the general discretization framework for any nonlinear equations. We can cast our Navier-Stokes equation, Euler's equation in this kind of format. So now our objective is that, as I shown in the projection-based reduced order model, we project them on a reduced basis. We call it as a linear manifold projections. So for that, what we need to do, we have to generate a set of high fidelity simulations. Say like U is the variable of our interest in the governing equations. In case of, it can be pressure, velocity, or any kind of fluid flow variables or any structural mechanics variables. We have to stack them up. And then we try to compute the modes out of it using singular value decompositions. So this matrix U can be broken into this we can get the capital U matrix from a singular value decomposition of this snapshot matrix, and this left hand side U matrix are the modes on which we will cast our solution on. So like we can get this reduced variable U by we can get this reduced variable U hat, and which is projected on a 5, like U is projected on a 5 space, and our reduced variable is U hat. And then what we do after we get this linear manifold, after we get these basis vectors phi, we project our governing equation on that reduced space. So that time and space discretized governing equations I have shown earlier on the general framework, which can be put or cast on a phi, and our governing equations will look like this. So of course, the linear operator will not cause any problem. So we'll get a reduced order linear operator AR from that. So it can easily be cast. But main issue happens with the nonlinear part of it. So even if you project your variables of your interest in the governing equations on the phi space, then still the computational complexity is not reduced because of the nonlinear operations. So, and also the operator which is associated with the input, that also can be easily cast into the linear manifold, given that, okay, this operation does not depend on the variables U. But if it is a nonlinear variable, if it is depending on the variable U, then also you have to handle it in a different way. So in the nonlinear part of the equations, when you project it on a governing equations, as I told, the numerical complexity is not reduced. So we have to use some further approach like hyper reductions or so for reduce the computational complexities. So there are several hyper reduction approach available in projection-based reduced order model. So there are a lot of literature available. Like one I have used is discrete empirical interpolations method. You can have a look. Okay. So now two types of test case I will be considering. One is a very linear structural equation, which is a mass spring system with a periodic lift and moment coefficient coming. Usually it can come from aerodynamics for aeroelastic system. But for the sake of simplicity, I have considered that it is a sinusoidal case, sinusoidal lift and moment forcing function applied on it. And if we discretize it, the time derivative using second order backward Euler, and then we can get the residuals after the discretizations, it looks like this, where x is h and alpha. H is the pitch and alpha is the plunge of the aeroelastic motion. Similarly, you can do the same for viscous Berger equation as well. So first you discretize the time derivative part using some forward difference, and then upwind scheme for the convective part, and some central difference for the linear part, diffusion part. Then you can get this discretized form. And then after that, when you project it on the phi space, as I told, after on the linear manifold. So for the time derivative part, it's not an issue. It's linear. On this diffusion term also does not cause any problem. It's the linear part. On the other hand, in the nonlinear part, in the convective part, so you cannot be able to, even if you project the U on a phi space, so your computational complexity is not reduced because you still have to compute the full. You still have to operate this still have to work on this nonlinear operation on the full computational domain. So the computational complexity is not reduced, and we apply DEM type hyper reduction approach so that we can reduce its computational complexity. So now idea is that how can we take the residual out of this kind of discretized equation and put it in our conventional deep learning framework. So as we know, in deep learning framework, you give an input and then it passes through a nonlinear activation functions, weight matrix, bias vectors, and you predict something. And then you try to minimize the loss, minimize the distance between some data that you have available. And that way you kind of train a deep learning network. But addition to that data-driven loss term, you can also add this residual arising from the governing equations. And even with a scarcity of data as well, with the addition of this equation, you can still will be able to solve the, still will be able to train the deep learning. So here just one comment here. So it is not a replacement of CFD, but it's a replacement of machine learning. So here we are still learning the way we were learning the conventional deep learning. So it's still an interpolation method, and its potential is only there in the prediction phase. So it will still be time consuming more than conventional CFD approach. And it is only be beneficial if we can use it for the prediction purpose, like at a different parametric point or something like that. So same thing can also be done in the context of LSTM as well. So like the one I have shown earlier, it is the ANN network. But LSTM network is a bit different from architecture wise. So you have to treat it in a different way, but pretty much same framework. So in case of LSTM, what happens? It is time dependent, both input and output. So if you have a input, say X, in case of semi-aeroelastic case, I have a pitch and plunge in the, sorry, I have lift and moment as an input and pitch and plunge, H and alpha as an output. So those are time varying things, time varying variables. So you have to give it in a sequence, unlike the NN case. So in LSTM, it is like lift coefficient at time step 1, time step 2 to time step times S will correspond to the lift pitch and plunge corresponding to the S time step. So you have to give a sequence of time, and the last time step will corresponding to the output corresponding to the last one. So that is how LSTM input output architecture is built. So like as you can see, the input is input is taken from first time step to S, which correspond to the output corresponding to S. So like CL1, CL2, CL3 to up to CLS, and then corresponding to HS or alpha S. And if you have how many types of input parameters you have, like in case of my aeroelastic case, I have two pitch and plunge parameter. Sorry, two parameter in the input, which is CL and CM. And I have two parameter in the output, which is the pitch and plunge. So again, then the story is the same. In case of LSTM2, so you give an input, and then and once you get the prediction from the LSTM cell, in the conventional deep learning, you can compare. You can minimize the distance with the data only, but here also you compute you pass the predicted value from your neural network, pass it to your discretized solver, get the physics-based residual, and try to minimize that too. But overall architecture is the same. So I'm not going detail of the LSTM architecture. You can have a look in any kind of LSTM framework. So good thing about this discretized PINN is that any kind of architecture can be used, because it only depends on input and output. So whatever input of your interest that you give in conventional deep learning, so like here CLCM or any kind of input or whatever output you are getting, so that you can use it because your PD is getting solved only using output only in a discretized way. So what is the advantage over conventional PINN is that, as I told you, existing forward solver can be used for ill-post and inverse problems. Another thing that I told, a flexible choice of input. So also, of course, you can use any kind of input in conventional PINN too, but it kind of eliminates the requirement of spatiotemporal input like X and T, which is required in case of conventional PINN, because you need to compute the derivative using automatic differentiation. But here, since we eliminate the automatic differentiation part and we try to get it from the numerical like discretized solver, So you don't need to worry about whatever input you are considering. And third point is that, like, if I already have some numerical data available from a discretized solver, so it's better we use the same discretization scheme so that my physics-driven loss term and the data-driven loss term, they do talk to each other. So like they are compatible, and we can see the loss term reduce very well, given that, yes, we are using the same numerical data and the same numerical discretization solver that we have used in this context. Okay. So now question is that there is the potential of this kind of approach can only be used. So if we are able to couple with a real external solver like OpenFOAM or DIL2 or something like that. So their main issue happens like two things where we need the computer, where we need the form of the PD or the discretization form, because in case of deep learning context, one is that while computing the AD-based derivative, that part we have eliminated it because we are computing it from the discretized solver. Another part in the optimization machinery, like we need to compute the residuals derivative with respect to the parameters. So if you cannot access the discretized form of it, you cannot compute the derivative with respect to the neural network parameters. So like we have two types of loss, as you know, data-driven loss, which is based on the data available, and one is the equation-based loss term. So for the data-based loss term, we already have a network. We already have a we know the functional form, and we can put it into our computational graph, because widespread is an outcome of the deep learning. So it is already there. We can use it in our computational graph. But here in the R, which is coming from the discretized solver, so it is completely has been solved in an external solver, which is OpenFOAM, and I don't know what discretization scheme has been used, and I cannot use that form in my deep learning, so that I can use it in my optimization machinery to compute the residual with respect to the neural network parameters. So for that, which is very important to update my neural network parameters. So I don't know. So now I need to modify. So the idea here is that can we modify the gradient term which is going into the optimization machinery? So like that. So like in the back propagation, we need this this derivative of gradients of L equation, which is the loss term based on the equation with respect to the neural network parameters. So this we cannot compute because using our conventional backpropagation approach, because I don't know that functional form. How does this L is a function of T? Because L has been computed in a completely separate environment, like in our C++ or whatever. So idea is that let's do a derivative on this, and you get it was R square. Sorry. It was R squared, so it becomes 2R del R by del P. And then the idea is that to break this del R by del P term, which is the residual with respect to the hyperparameter P, into these two chain derivatives, which is the del R by del Y predict and del Y predict by del P. So now these things also we can compute. Yeah, so now del R by del Y predict by del P, this one you can compute from your computational graph, because Y predict is an outcome of your deep learning. And del R by del Y predict, this one you compute it from the C++ or the external solver that you have. So R is basically the residual that your OpenFOAM or DIL2 is computing, and Y predict is the input that you are giving. So imagine in Navier-Stokes equations, you give the prediction of the P, and out of the continuity equation, you are getting the residual R, and you are computing del R by del Y predict, which is the del P predict. So at lot of numerical cases, like is the Newton solver or something, you anyway have to compute this del R by del Y pred, so which you can directly import from there, or you can very easily implement in both in the C++ side, also in the PyTorch side as well. So, and also addition to that, it is not that difficult, that computationally expensive to compute, because the residual at say particular grid point or so, it only dependent on the variable only at the surrounding grid points. It's not dependent on the whole computational domain grid point. So actually that's how you can reduce the computational complexity of computing these Jacobians. So this is the idea. So you take not only the residual from the open form or DIL2, you also take this Jacobian from the open form or whatever external solver you have, then you are all set. So now this is detached from the computational graph. This is detached from the computational graph. So basically, when you compute the derivative, if you del parameters, so basically it only gets applied on Y predict. So idea is that instead of sending R square, that this L equation term in the back propagation, send instead this one, this modified term in your back propagation. Then you are all sorted. Then actually you can then nothing is compromised. You can get the exact gradient term that you earlier used to get. So this is the algorithm that we will be following. It's pretty much straightforward, like normal deep learning network. So you have you start with some benchmark data set. You have some input. You know at how many data points you have. You know that how many for collocation point you will solve your equations. Then you initiate your weight matrix and bias vector. And then when the epoch is less than a number of epochs, like what is a conventional deep learning, you compute the Y predict here. You compute the Y predict and pass it to the neural network from the neural network, and then pass it to the external solver. The external solver will compute the physics-based loss term and give it back to the PyTorch. In external solver, you compute the residual, and then you compute the loss term based on the equations. You compute the loss term based on the data. And then you compute, then as I told, from the external solver, you not only have to compute the loss term based on the equation, you also have to compute the Jacobians. Although it's a sparse Jacobian, but it is still expensive to compute at each epoch. So I kind of updated that Jacobian not at every epoch, but say at some interval of the epochs. So you decide how many intervals of the epoch you will update your Jacobians. So for the test case I have, so probably 100 or 200 iterations was enough. Maybe it is more convection dominated flow. So if the Jacobian contribution is more prominent, then you have to update it more frequently. But we can reduce the computational time a lot by updating the Jacobian at an intervals. So we fixate the Jacobian at that interval, and then compute the LD space, which I told you to pass it to the backpropagation instead of the actual loss term. And then you compute, and then you update the neural network parameter based on that. So that's the major story or major takeaway from this talk. Like when you actually couple it with the external solver, so this is the way you can solve these problems. And so now I'll show some of the examples. Like I have applied it on like simple structural cases. So this to a linear pitch plant system with lift and moment coefficient as an input, and both lift and moment coefficients are sinusoidals. I think CL is sine 10t and CM is 20 radian per second is the frequency. And if you look at the error plots, and if you use only very small data points, when I say data points means I am using only numerical data as one, numerical data at 3 points, numerical data at 200 points, numerical data at 1000 points. So total I have 1000 time steps. So total now have 1000. I have total time step of 1000. So I'm reconstructing the whole temporal domain now using only 1, 3, 200 and 1000 data points. So of course, ANN, DSPIN, AD, all the pins have been performed very well when you have less amount of data. On the other hand, without any data, only the deep learning part, ANN and LSTM, without any physics, they are performing very bad. But as we keep on increasing the data, then all the methods like be it without physics or with physics, they are kind of close to each other. And LSTM pin is performing very well than ANN pin for all the data points, and that also given on the hyperparameters we have used, nothing concrete on that. So if you change the hyperparameters, probably one can surpass other. So we cannot conclude that, okay, this is better, this is good or not. So I'm probably not selling LSTM pin here, probably selling normal discretization based pin. So it is just a coincidence that it has been better based on the hyperparameter that I have chosen. But on the other hand, the AD based pin is showing is a little bit much error than the discretized pin. And its reason is being that, as I told, what happens like I have generated the numerical data based on a typical discretization based discretization scheme. And AD based pin does not talk to the way I have generated the numerical simulation data. So that's why the AD based pin is showing some more error than the discretized pin. And as you can see, the error quickly, the MAC loss term quickly decay in case of discretized pin, but in case of AD pin, it does not decay so fast. If we use the more amount of data, like 1000 point or so, then these incompatibility of these two loss term becomes more prominent because so the numerical data, the way we have generated it, the discretization scheme I have generated it, I'm trying to add the physics-based penalty using a completely different way of using solving the PD equations. So in case of discretized pin, it has been in the 10 to the power -3 regime, but here it is in the above 10 to the power -3 threshold lines. So that's probably give us the reason why the AD based pin is above the discretized pin. And we have also been able to use it for prediction purpose as well. So like when I have only one data point, which is the initial value I have used, and then equation solved at the 5 points. So like first 5 points, I have only solved the equation and I have only first numerical data. The previous example, I have solved the equation for the whole domain. So it was kind of a reconstruction. But here I have also solved the equation at first 5 points, first 50 points or 500 points, and trying to predict the rest of the domain as well. So for the ANN pin and so for the even when I'm using the 50 points, then ANN pin has been able to kind of follow the trend, but LSTM pin did not work so well. But when I'm using 500 points, then ANN and LSTM pin both has been able to follow the trend as well as the small undulations as well throughout the computational domain, both beach and plunge. And so then how much time left, Anna?
Yeah.
Oh, 10 minutes. Okay. So then I have shown it for the Vargas equation with AD-based derivative. The one I was telling is that, so since the way we have generated the numerical data and the AD-based derivatives are not compatible to each other. So of course, I have got some other solution from PINN framework, which will be different from the discretized from the numerical discretization that I have used for solving the Vargas equation. So of course, at the end of this upper right corner of the spatiotemporal domain, it will show the much higher error. but this error is with respect to the discretization scheme I have used. Probably if I use something else, probably it would have been closer to AT-based derivative. So it is also nothing confirmative. Yeah. And also NN dispin and LSTM dispin, when I'm comparing with the same discretization time derivative scheme I have used in the PINN solver, of course, the error will be very less. And if we compare with LSTM dispin and NN dispin, of course, NN dispin shows much maximum error like than the LSTM dispin. And surprisingly, if we keep on increasing the data, like when we are using all the data set, our even with the data-driven approach, surprise or outperform the physics-based PINN. Probably because we are adding this physics-based burden on top of this, which was not required in the very first place. And we are trying to reduce some additional computational burden in the loss term, which was not required. So that also suggests why it is, why when you have more data, just conventional data-driven approach is much better than the physics-based approach. And these are the error plots that I have shown. Major key takeaway that, okay, NN dispin, when I'm using only one data point, it's in the range of 0.016 is the error. In LSTM, it is a bit less. But however, without any physics, the error will be much higher. And when I'm using more data points, then of course, this error associated with data-driven approach is much less than the physics-based, not much less, little less than the physics-based approach. And in the prediction phase also, we have been able to capture good error bound when we are using 500 data points, 50 data points, than the 10 data points for the predictions. And of course, it will be completely matched with the actual numerical solver because the same derivative schemes I have used both NN and LSTM. So of course, and then another approach of reducing the computational time of PINN, or a few days back, we had a talk like how to ensure that the loss minimization term will be guaranteed for PINN. So of course, there are a lot of theoretical approach can be addressed in that context, but very simplified and straightforward context approach will be reduce the computational burden. So so if you can reduce the computational burden on the optimization machinery, that okay, I don't need to reduce the loss term associated with the full computational domain. Instead, we only solve at only 10 points, 10 collocation points. Of course, my optimization machinery will perform much better. Now, of course, we can do theory on top of this a lot, but this is a very straightforward and way of thinking. So that's why instead of taking the full residuals from the Burger's equation, I project it on a reduced space as the equations I have shown, and then use it in the PINN physics-based term. And as you can see, the time has been slightly reduced, not in a linear way, because of course we have to do other operations as well in the reduced order formations. So when I'm using 10 modes and 10 dying points, then actual simulation, when it takes around 1200 seconds. In case of reduced form, when I'm using 10 modes, it's taking 937 seconds, which is not exactly half, but somehow 3/4 or something. And when I'm using 5 dying points and 5 dying modes, then also it is not exactly been half from 10, but slightly close to that. And we can use this approach as well. But I will talk about the shortcomings of this POD-based projection and use it in the context of PINN later. But first, I would like to show it when I couple it with the external solver, which is completely detached from the PINN framework. So then also it shows same kind of error, which is very less, using that additional Jacobian term that I discussed few times back. And here in case of Burger's equations, I have updated Jacobian at 100 epochs, 500 epochs, 1000, a total was 3000 epochs. And total 6,000 epochs, and even if I update it with 2,000 epochs as well, the loss has been minimized. And in case of NN PIN with only 2,000 epoch, when I update the Jacobians, then the residual goes up, it start diverging. But in case of LSTM PIN, they all drop down quite well. So for more nonlinear problems, probably we have to shrink down the epoch updates. But but this is but for this problem of interest, this does not actually increase the time at all, not at all, but very insignificant amount as compared to the training when the network is not detached at all, which I term as a without loss term modification. So as you can see, they are almost kind of look like each other same. So now the future work that I am considering is that coupling actual real CFD solver. Right now, both are written in PyTorch, and I kind of detached it, but trying to couple it with Ithaka FB and our PINN solver. And the main problem with the POD-based projection is that in the POD-based projection, we need the full data set for the projections. And then in the potential of the PINN is that we can use sparse data set. So it is time consuming than CFD. Then why we are using PINN? Because we can sparsify the data set and use it for the predictions. So, and if we use POD projection in the very first place and then apply it on the PINN, in the POD phase, we are still using data, the full spatio-temporal domain, or in the parametric space in a dense way. So the potential of the PINN is not realized there when we are. So of course, after that, in the reduced coefficient, when I'm learning in the PINN, I can reduce the data points. But in the POD projection part, in the very first place, I am using lot amount of data. So the effectiveness of the PINN is not realized over there. So Gabriele is now working on using some convolution autoencoder based manifold projections, where even without data or using very small amount of data, we can project it on a reduced space so that our full potential of the PINN can be realized, both in the projection based as well as in the feature learning space. And third, I am also involved in an industry scale problems like multi-phase problem with reaction kinetics. And of course, these methods potential can be realized when we solve these forward solvers like SU2 or OpenFOAM or DIL2 in the inverse problem, where actually forward solvers are not good enough. So yeah, that's it. We should have
now discussion time. So from online, you can submit yourself and ask them. Yes.
You go back on slide 19.
We still have, really you have questions? Yeah. Okay.
No, the one where you show the Burger trajectories. Here, so what's benchmark in this case?
Yeah, the time derivative that I have used, like with the forward differencing in time and the central differencing for the linear term and the upwind scheme for that.
And you're saying
so with that benchmark, it is showing that error.
So basically it's saying that the finite difference one.
Yes, and
it's away from the actual differentiation.
yes, yeah.
But actually different
which is coming from the AD based PINN results, and the one I have benchmark means the numerical derivatives part.
Okay, which has error.
Which also has error, yes.
Okay, because automatically, the thing that I didn't understand is that you're saying that automatic differentiation brings error or doesn't bring error? Because usually automatic differentiation.
No, I am computing the error with the automatic differentiation based PINN result with the numerical scheme that I have used to solve the Burger's equations.
Oh, yeah, but I'm not seeing what's the, like, I don't understand if you're saying that automatic differentiation is bad because it produces error. Or
all I'm saying, it is not matching with the with the numerical solver that I have used in the very first place to generate the data. So probably this is close to the actual results, probably, I don't know, but the kind of CFD solver I have, it is not matching with that because the derivatives I have used in the scheme, which is not actually same as the, yeah.
I get a feeling this AD is much more accurate than the numerical scheme that you're using for the AJS definition.
Yeah, probably.
AD is exact. So,
So this,
but
the scheme that you introduced might be a bit, but anyway.
Sorry, but this AD refers to the solution given by neural network
Neural
to train
network, yeah.
on AD.
Yes.
So AD is just part of the network.
Mhm.
That's the prediction of the network. It's not comparing derivatives directly.
No, it's not computing the derivatives, computing the derivatives, yeah.
You get to the shortcut.
Mhm.
When you're training a PIN,
Mhm.
it doesn't, I mean, there are bounds to it that says that you're not going to approximate close to the shortcut that well. So I don't think it's a problem of AD, but it's more a problem of finding the PIN.
Mhm.
I have a curiosity, Rahul.
Yes,
Have you ever tried, I mean, if I understood correctly, you are using both the two loss terms,
yes,
the data and the physics one.
yes,
But in principle, if I understood correctly, you should be able to run just the physics condition on your numerical solver somehow. So you just read
Yes,
some
yes.
random number,
Actually,
you
when I
evaluate the
use-
residual, and
Yes.
you come back to the Python to train a bit.
exactly.
Have you tried to do that?
Yeah. When I use data used one means it's only the initial conditions,
Uh,
which is at
Okay.
equal to
So
zero.
basically you have
yeah,
just the
it's-
initial condition
yeah,
and then
and the
you
physics,
yes. Which is better, sorry?
Mhm.
Which is better in your opinion? I mean, I don't remember the error.
Better
you
means
showed.
the discretized pin or the conventional pin, I'm saying, you are saying, or the two types of discretized pin I have used.
No, the one just using also the data you have collected from simulation
Yes.
and the one without putting any basic
Yeah,
information
so-
about the data.
Yeah, so like as you can
Just
see
the
from
initial
this
one.
here, because the two types of I have used, like two types of test cases, they are very simple cases. They does not say much of it because the equations are very simple. But of course, as you can see, if I keep on increasing the data points, the error is dropping a bit.
Okay, but at the beginning, so you have 20% error, right?
Yeah, but that when I am not using any physics at all. So you can look at here. No, the relative. So
I'm looking at the blue line.
yeah.
Correct.
So it is at around 0.15. No, I think it should be the actual error. So like I may be mistaken here. So it is the actual error with respect to my data. Let me check. Let me check. Probably it is
No, but
relative
it was
error.
just a curiosity.
It's an
because
absolute error or relative error. I have to check it.
Sometimes with
Mhm.
just the standard PIN,
Mhm.
it happened that
Mhm.
if you plug two terms of losses, actually you are not gaining anything.
Exactly.
Okay, so you have the same basically feedback also here.
No, you are saying when you are using both data and physics, sometimes it deteriorates.
Yeah, it is not really improving, adding new term of losses.
Yes. So that's contributed by these two things. Like when you are the data that you have generated using a derivative scheme, probably is not talking to the derivative that you are using in the physics-based solver. So,
So
like
I'm not. I mean, I never tried with some numerical solver in between.
yeah.
So during my example experiment, basically,
Mhm.
I know the true solution.
Yes.
Everything is analytical,
Yes.
so I know everything
Yes.
the data.
Yeah.
I have no the problem of the grade. I mean, evaluating the gradient
Mhm.
through a numerical solver. So I don't think it's the case.
Mhm.
But yeah, you have two terms of losses, so the optimization problem is definitely more complex.
Yes.
And actually, yeah, you fail to find the
Yeah.
Okay.
It kind of adds some additional burden. So I don't have a definitive answer. So
Okay.
sometimes
No, the same. Just
Yeah.
a question if you
Yeah.
feel the same. Okay.
Yeah, so sometimes it deteriorates the problem. So we instead of making it much better because your computational burden increases.
Exactly.
But majorly, I feel like the issue is coming the data that you have and which has been generated by some numerical discretization scheme is not kind of matching with the numerical derivatives you have used in the PINN
It
context.
matches, but I mean, with a certain precision.
Yes, because especially the numerics is erroneous.
Then
Yeah.
get lost in the
Yes.
indirect terms.
I mean, numerics is erroneous because if you use finite difference, finite whatever, it is much more erroneous. But issue is that the data I have and the derivative scheme I am using, they are talking to each other or not. That is even worse. And they should talk to each other for a better residual minimizations.
I have another curiosity. LSTM, this pin, and then this pin. The time is discretized also at inference time or just real training? The time domain is discretized.
Yes.
Can you interpolate because PINN, for example, they can use captured data points, right? I understood that you use captured data points for the spatial domain. Can you do it also for time?
Yeah, you can do it for time as well. Like the way I have used it, like say like now these are my inputs and these are my outputs, right? So like I have CL1, CL2 to CLS and then associated with AJS. So you take say first point, third point, the first line, third line, and then rest of the thing you try to reconstruct. So you can take, but given the fact that, yeah, I mean, it's just in the training phase, you just take this data as your data point, these two lines, and then rest you can predict.
Right. So let's say if
you can use it for interpolation, yes.
You can
use it for interpolation.
Okay.
In those cases, when your input and output are different. So LSTM people usually use the same input and output, right? So that's why it is difficult to use it for interpolations because you have to know things which you don't know if you're in that because both input and output are same. But here I know lift and moment coefficients completely, and my output is different, pitch and plunge. So I can take some intermediate data of lift and moment coefficients and put them in a sequence and get the corresponding pitch and plunge. So I'm saying in a nutshell that, okay, I have now 10 this type of input, right? So I take first one and second one for training, and I can use till third one for predictions. Because third one is consisting of lift and moment coefficient in the input, which you know already. The things you don't know is the pitch and plunge.
It's not.
I know lift and moment coefficient, it is sinusoidal. I don't know pitch and plunge. So if you use only first and second for training, you can use this, you can put it in a same sequence, your lift and moment coefficient and predict your pitch and plunge. But problem will arise in the way people address this LSTM. They use this lift and moment coefficient itself in the training.
Yeah, usually.
So then you cannot use it for interpolation. Then only you have to use it for prediction.
Okay, so basically you use the coordinates
Yes.
and you shift. So you arrange it in an ordered way.
Yes.
And then you shift it.
Yes,
and
yes.
You can do it for whatever coordinates.
Yes, yes.
Ah.
Yeah, that's the thing, because if you know that, like, okay, see it, if it was the same input and output, so when you want to give input the third line, so that part you don't know, because that part you are supposed to learn it from here or here. So it is a problem for interpolation in case of LSTM when your input and output is same. But if they are different and you know the input, then you can still use LSTM for interpolation. That's a key takeaway. Like ANN. You can still use it like an ANN.
Just a quick question. What is your sequence length
In my case, I have used 10. 10.
Ah, okay.
10. 1,000 is my
10
total time step and 10 time step as.
And if you tried like with more time steps or less, have you seen?
No, those things I did not check yet. Like all that's what I'm saying. Like right now, LSTM pin is coming better than NN pin, but I cannot say that it will come always better. So I cannot take credit on that.
We can thank Rahul again.